Carl Friedrich Gauss, an early 19th century German mathematician and scientist, he's the namesake of over 100 concepts across mathematics, physics, and astronomy. One of those concepts is the Gaussian distribution, also known as the bell curve, though several distributions actually are bell-shaped, but it's the most famous one. It's also known as the normal distribution. So just as we used a method in the NumPy random module to generate a uniform distribution, we can do the same thing to generate a Gaussian or normal distribution. Again, we can sample, say, 10,000 points, and we'll put those in the vector x. And then we'll use the same Seaborn disk plot as we did for the uniform distribution to plot our Gaussian or normal distribution. So this is that classic bell curve. Looks like a bell that you could ring. And if you want to see that bell shape even more, you can turn on this kernel density estimate. So you can set that to true as a disk plot argument. So this kernel density estimate gives us this line outlining the shape of our probability distribution. So when the normal distribution that we're sampling from has a mean of 0, right? So its expected value is 0, and it has a standard deviation of 1. So remember the standard deviation that we studied earlier on in these live lessons, right? So that measure of variance. So if the measure of central tendency, the mean, has a 0, and the measure of variance, the standard deviation, is 1, as it does by default with the NumPy normal method. So this here meets those criteria, and we can confirm that by looking at the sample mean, which is indeed very, very close to 0. So again, following the law of large numbers, if you increase the sample size, your mean of this particular sample, so we've sampled 10,000 data points from a normal distribution with a mean of 0 and a standard deviation of 1. If you increase the number of points that you sample from 10,000 to 100,000 to 1,000,000, this mean will get closer and closer to 0, typically. So this proves definitively for me that we're close enough to 0 here for us to meet that one criterion of the mean being 0. And the other criterion that I'm talking about here is a standard deviation of 1. And yeah, we're pretty darn close to 1. So if we meet those two criteria, the mean of 0 and the standard deviation of 1 for our Gaussian distribution, for our normal distribution, we can call that a standard normal distribution, also known as a standard Gaussian distribution. So normal distributions can be denoted with this math calligraphy font as n. So a capital N in this math calligraphy font, and then an open round bracket, and we put in mu for the mean of the distribution, the population mean that we're sampling from. And then we put the variance in the second slot here after a comma, and then close the brackets. So this standard notation for the normal distribution allows us to annotate the standard normal distribution as fancy calligraphy font N 0, 1. And note that this is variance here, and I've been talking about a standard deviation of 1, but the variance is equal to the standard deviation in this special case because 1 squared is equal to 1. So normal distributions are by far the most common distribution in statistics and machine learning. They are typically the default option, especially if you have limited information about the random process you're modeling, because, first of all, normal distributions assume the greatest possible uncertainty about the random variable they represent, relative to any other distribution of equivalent variance. Details of that are beyond the scope of this tutorial, but it's a huge strength to the normal distribution. The second reason why we often choose a normal distribution is that simple and very complex random processes alike are, under all common conditions, normally distributed when we sample values from that process. That's a mind-blowing thing, and we're going to talk about that a lot. So since we sample data for statistical and machine learning models alike, this so-called central limit theorem, which we're going to cover in a huge amount of detail next, is a critically important concept. And it's pretty mind-blowing. So the idea here is that no matter what random process we're modeling, if it's ultimately a uniform process or some other kind of distribution, when we sample values from it, the distribution of those samples will be normally distributed. All right, so it's crazy, I promise. You'll see. Nice, so some real world examples of normal distributions other than the central limit theorem that we're going to talk about in a lot of detail next is, say, the probability of getting heads across n tosses. So we've done this already, right? So we've looked at the probability mass function that we get if we do 5 coin tosses. And so we talked about this a long time ago in these live lessons. We were tossing 5 coins and seeing how many are heads. So we talked about that way back in this statistics section. When we generated this, look it, it's normally distributed. Ha! But we can see that normally distributed nature even more so if we increase the number of coin tosses. So, for example, if we increase from 5 coin tosses to 100 coin tosses, let's do that here. So let's run 10,000 experiments, and in each of them, we will do 100 coin tosses with a fair coin. And so this is the same code that we used earlier to generate that plot that I just showed you with n equals 5. But we're rerunning that code now with n equal to 100. And let's see what kind of plot we get. Voila. It is very nicely normally distributed. So there's an example, a real-world example of the normal distribution in action, the probability of heads across, any number of tosses, especially if it's a large number. The sum of dice rolls, if we have, or even a die rolling a single die, that also follows that behavior. The height of adult women, the height of adult men. And so if you put those together, you actually get not a normal distribution because there's 2 peaks. So we'll talk about that kind of situation later where you have multiple distributions combined. But if you look in, say, the United States, at all adult women, their heights follow a normal distribution. And same thing for all adult men in the United States, follows a normal distribution. And even very complex behaviors like scores on an education test, like in the US, there's a common standardized test called the SAT, and scores that people get on that test follow a normal distribution. Great, so there's your introduction to the normal distribution. Up next, we're going to dig deep into that central limit theorem idea that we just touched on in this video.